I put our website up here because you can find out more about the projects I'm talking about today, including downloading the report, all the technical reports, and a lot of actual raw data you can download off our website. Our agency is called the Southern California Coastal Water Research Project, but it's a really big mouthful. So we all just call it SCWRP, and that's how it's literally known around the country. So we actually talked about changing names, and our Board of Commissioners said, no problem, but don't change the acronym. Yeah, so we've actually been around almost 50 years. We're actually what's called a joint powers authority. It's a public agency, and it's when multiple public agencies get together and form a new public agency because they have a common need and a common purpose. So the best example that I've heard is like a county fire authority, where the county and the small cities all need a fire department, but they all, not all of them can afford it. So they all kind of pitch in and form a fire department that covers the whole county and all the cities. And so that's what happened with SCWRP. It was back in 1969, so it was right before the Clean Water Act, and these municipalities saw that the environmental regulations were going to be coming, but they didn't know much about the environment. So they formed SCWRP to help learn more about what the environment is and what they're doing to it. So our mission is really to understand the impacts of human activities and then communicate that to decision makers. So hopefully they make well-informed decisions. And so we don't have to do all of that science ourselves. We just need to help facilitate it and build scientific consensus, because if there's one thing I've learned is that decision makers they'll move forward and make decisions when the scientists speak in unison. But if you have scientists, what we call the dueling scientists, they just freeze up and won't do anything. So here's our member agencies. There's 14 of them, and it's an interesting group that makes up our commission. The first 4 on this slide represent 4 of the 5 largest wastewater dischargers in the country. I mean, cumulatively, it's over 1.5 billion gallons of treated wastewater that gets discharged every day. The next 4 are the largest municipal stormwater agencies. There's one thing we have in Southern California. It's a big city. So it's like 28 million people, and it's literally paved for hundreds of miles, hundreds and hundreds and hundreds of miles. The next 5 agencies are the state regulatory agencies. And if you're unfamiliar with the regulatory structure in California, the main state water board is in Sacramento, and they kind of do a lot of the policy development, and then they have regional boards which do the on-the-ground implementation of regulatory enforcement. And so they work together, and we have both. And it turns out there's 3 of these regional boards in Southern California. Then we have the regional EPA, and we have another group called the California Ocean Protection Council, which is an affiliation with the Natural Resource Agency. So the council, well, I won't get into the details, but it helps us reach out to the natural resource side of the house. The good thing about our SCWRP member agencies is it's like the chief engineer at the treatment plants. It's the chief flood control engineer at the stormwater agencies. It's the executive officers of these regulatory boards, right? So we're dealing with the highest level decision makers. And so as a scientist, it's really fun because our science goes directly into their decision-making process. We don't make policy. We don't advocate policy. In fact, that's our biggest, if we start advocating, then we've lost our biggest virtue. But I can tell you that when we put the science in front of them, they immediately start thinking, how am I going to use it? So this is a picture of our study site, one of the study sites I'm going to talk about today. I want to start off with just some basic facts about Southern California beaches. There's a lot of people that go to our beaches. Right? We estimate somewhere 175 to 200 million beach visits per year. So that's more than Hawaii, that's more than Florida, that's more than New Jersey. It's more than all of those combined. And it's a huge economic engine. I mean, it's over $40 billion a year of just kind of ocean tourism. So we also do a lot of beach monitoring there, right? Because, that's what's driving that economy. A lot of them are coming to the beaches, just like I showed in that last photo. And so we collect a lot of samples for bacteria. And the whole idea is to monitor for public health. There's a kind of a misnomer down in our region that our beaches are really, really dirty. And it turns out, and I'll show you in a minute, that the water quality really isn't that bad. It just turns out they take most of their samples next to storm drains. So the way you read this graphic is the x-axis, the one along the top there, is the percent of beach mile day. So it's a function of both time and space. So just think about it as percentage of samples. Just for, the bigger the bar, the worse it is. And when you look at all of our beaches, the rate is actually quite low. It's down around 3%. 3% of the time, it might exceed a water quality standard. But if you're directly in front of a storm drain, more like a third of the time it's exceeding standards. So it's good that the public health agency should monitor right in front of storm drains, because as a public health monitoring program, you want to be in your worst places. The problem is that's the only place they monitor. And so everybody thinks that our beaches look just like the end of a storm drain. So when I have people come visit me down on the South Coast, they go, Ken, you're the water quality guy. Which beach should we go to? And pretty much I always tell them the same thing, which is any beach you want, just don't swim in front of a storm drain. Unless it's raining. So we did the same study doing monitoring across all of our beaches, only right after storms. And now what you can see is not only does the exceedance directly in front of storm drains go up to north of 80%, but pretty much all of our beaches look like storm drains. And the result of this is the county health authorities just issue blanket warnings. Do not go in the water for 3 days. And they put it in the newspaper, they put it on the radio, and I'm going to tell you that is common knowledge amongst all the folks that live in Southern California. If you ask them, should you go in the ocean after it rains, they'll all tell you, yeah, not for 3 days. And so you can see that can have a huge economic impact. So let's talk about what the issue and then what the problem is. How many people in here deal with fecal indicator bacteria? Okay. Any actual microbiologists? Excellent. Any public health experts? Okay, great. So I'll talk a little bit about bacteria. Some of it you'll know, and then feel free to ask questions. So beach water quality, in fact, all water quality for fecal contamination is based on these indicator bacteria, things like Enterococcus, fecal coliforms, E. coli, total coliforms. These are all sounding familiar to you. Turns out these are not the things that actually make you sick, right? They're indicators that co-occur with the pathogens that actually make you sick, right? So in your gut, if you're sick, you have pathogens like viruses, and you have a lot of these indicator these like Enterococcus, which are natural in your system. You're actually glad they're there. The problem is that it's really easy to measure these bacteria. It's just really hard to measure the viruses. So that's why they go with the indicator bacteria. And then the projects that try to link these indicators with actual human illness are called epidemiology studies. All of these studies, the ones that we've done at SCCWRP, the ones that EPA have done in order to generate the water quality standards, are all done in the summer, and they're all done at really beaches impacted by sewage. And they also know there's going to be a lot of people in the water, which is key to getting some of these epidemiology studies done. Just looking for even small increases in health risk, you need a very large sample size. So the problem is, at least in Southern California, our sanitary systems and our stormwater systems are separate. We don't have combined systems. We've got separate systems. And so that's great, because even when it rains, we know the sewage is going to the sewage treatment plant and getting cleaned up before it gets discharged, that 1.5 billion gallons. But the stormwater receives zero treatment before it gets discharged directly to our streams or directly to our coast. We see, like you saw in that stormwater graphic, it contaminates all of our beaches. And so the problem is those indicator bacteria don't come just from humans. They'll come from any warm-blooded animal. Birds, dogs, cats, pick a mammal. Okay? And so there's an assumption if it's not sewage, if it's really just a bird or a dog, it might not have as many of those pathogens in it, right? So that the relationship between the indicator and the pathogen are now changed, and probably less of a risk if it's not human, right? If it's not sewage. And so I don't know about you, but down in Southern California where our beaches are prized, there's a lot of regulatory pressure. So you guys know total maximum daily loads? Does that ring a bell? Oh, everybody's shaking their head. Yeah, I know what a TMDL is. So we have lots of TMDLs on beaches for bacteria, and the regulatory kind of deadlines are on the horizon. So for the people online, I'll repeat the question, which is how do we know they're separate? And what's the history of the separation between our sanitary systems and our storm drain systems? All right, so I'll just say it. You guys get a lot of rain up here. We don't get a lot of rain down south, which is why everybody wants to come to our beaches. So, but when it does rain down south, it's flash flood. And so from the very beginning, they've been separate because our sanitary systems can't handle the flash flood. And so yes, there probably are some cross connections. There probably are some leakage. We probably do have sanitary overflows. I can guarantee we do. We keep a record of all our spills. So, but they're purposely not connected. What's interesting is while most of the country, I mean, we're kind of the rare exception, most of the country has combined. And as they start to move through and figure out what they're going to do with their CSOs, they're starting to separate them. In Southern California, one of the reasons our dry weather bacteria is so low is we're actually doing stormwater diversions into the sanitary. We're starting to combine them. Reverse, so it's funny how when you got one, you go the other. The question for the folks online, the question is, do we have any septic tanks in Southern California? And the answer is yes. So we still have areas with septic. The vast majority of the area is on sanitary collection system, but we definitely have areas with septic. So everybody knows Malibu. Malibu is completely on septic. Malibu, it's their growth control measure. They also have a TMDL for bacteria on their beaches. Know that fixing any of those things are really, really, really expensive. The kind of numbers we're talking about for that some of the municipal agencies are in the tens of billions of dollars to try and remediate these things. And we're talking about horizons for compliance that are 5 to 10 years. So I put this picture up. It was on one of a kind of surf forecasting website that a lot of people go to called Surfline. And it pretty much tells the whole story. If you know anything about surfing, then you know that wave looks perfect. And then it's got this sign in front of it. And so there was a whole article about our study, and it got a long blog reply after. And I just pulled one from Mikey Boy, who summed up what I've heard. I mean, I've interviewed now probably thousands of surfers, and this is almost a universal response, right? Which is, I know I'm not supposed to go in for 3 days, but if the surf is good, I'm going in. And some of them will say, I never got sick. Most of them say, maybe, I don't think I got sick, but I know a guy, right? He got really sick. So, but I'm still going in because essentially they're making a risk-benefit decision. They know what the benefit is, but they really don't know what the risk is. So that's why we started our study. We basically asked 4 questions. First one, is surfing associated with an increased risk of illness? The second is, does that risk of illness increase when you go from dry weather to wet weather? The third was, is there an association between enterococcus, the thing they're routinely monitoring, and the illness that we observe, particularly in that wet weather? And then the last one is, well, what's the right level of enterococcus? Is our current standard the right standard, right, in terms of public health protection? So there's a few things to note here. The first one is this kind of dramatic increasing in the complexity of the questions. The other is, it's all focused on surfers. So you ask, why surfers? Well, it turns out surfers go in the water by the thousands, by the tens of thousands during the winter. That's actually when our best surf is. And some of the best waves are immediately following storms. So we don't necessarily see a lot of little kids going in the water during the winter. They're going to Legoland or SeaWorld or Disneyland. So, but these surfers, I guarantee you'll find them every time. A question. Okay, so the question was, do we have shellfish, we're worried about shellfish contamination from the bacteria. So the answer is not as much as the actual body contact. So we do have some shellfish hatcheries, some commercial shellfish hatcheries, but they're more in the minority. That's not the driving regulatory issues. It's definitely body contact recreation. All right, so before I show you any data, I'm actually going to give you the answers to the questions. And then I'll show some data to help support the answers I'm about to tell you. So the first one is, yes, there is an increased risk of illness from surfer just going in the ocean. So it doesn't matter what the weather is, what the water quality is like. You go in the ocean, there's actually a slight increase in risk, right, of contracting an illness. So it turns out that that risk actually increases a little bit more when you go from dry weather to wet weather. There actually is an association between enterococcus and illness levels, but only during wet weather. Turns out you don't see that during dry weather, but during wet weather you do. And so even though you see people getting sick, they're more sick in wet weather, and it's related to enterococcus, it turns out that the illness level is actually lower than one would predict, especially based on current standards. So let me show a little information. So the answer, so the question was, is enterococcus the only indicator bacteria that we looked at? And the answer is no. We looked at fecal coliforms and total coliforms, and I'm mostly sticking with enterococcus for two reasons. First of all, the EPA's new water quality criteria is focused exclusively on enterococcus, and the second reason is all three indicators showed relationships. Enterococcus is just the best example because that's the one that exceeds standards the most frequently. So let me talk about the basic study approach. We recruited hundreds of surfers into the study across many beaches in San Diego. And we had them self-report their surfing activity and their health symptoms and other confounding factors like, did you eat raw shellfish, and anybody else sick at your house, those kinds of questions. We followed them weekly through a cell phone app. We'd have them sign up and give us a text number or an email, and we'd send them a tickler every Tuesday. And if they went for 4 weeks in a row, we'd give them a gift card to an online surf store. So at the end of that, we had more than 33,000 days of follow-up and over 10,000 surf sessions. So, and what we do is the interesting part of this design is that way that allows you to kind of follow a single surfer and compare them, that same person to themselves when they were surfing compared to when they weren't surfing, and then compare that same person when they were surfing in dry weather to when they were surfing in wet weather. So each person kind of serves as their own control. But we're looking for really very small increases in illness rates, right? So you need very large sample sizes. And then we went to 2 beaches in specific, and we called them our sentinel beaches, because at those beaches, we collected a lot of water quality information, both along the beach and in the discharge. And so I just kind of put this slide up to just kind of give you a sense. I say you need to collect a lot of data to look at very small changes. It turns out that the number of exposure events, around 10,000, makes us about the second largest epidemiology study that's been done in the last 15 or 20 years. So the rest of these are either ones that SCCWRP has conducted or that EPA has conducted to help support their water quality criteria. So I'm feeling pretty good about that. We gave away a lot of gift cards. I want to spend just a minute or two talking about a little bit about surfers. So I don't know how you guys envision surfers, but the way they've been described to me is, those surf bums, right? They're usually thinking, usually not nice things. Here's actually the true cohort characteristics that at least we recruited into our study. 80% are male, 3/4 of them have jobs, 2/3 of them have a college education, and the median age is the mid-30s. Our oldest surfer actually was in his 70s. So these are professionals, and it turns out they're actually very dedicated athletes, right? 80% of them surf at least every 3 days, we had a full third of them that surfed every day. And when they go surfing, they'll surf for, half of them will surf for up to 2 hours. So these are, I mean, if you think about somebody who's like an avid runner, who here likes to run? Anybody jog? Okay. So could you imagine running every day for 2 hours? Yeah, that's a pretty, yeah, these are professionals who are dedicated to their sport. It also means they're exposed a lot, right? All of them pretty much dunk their head, and over a third will swallow water with each surf session. That's the primary route of exposure to contaminated water quality. Now that I've given you a sense of the study and what surfers look like, a mental image, I want to talk about the results. And so this is the probably one of the more important key graphs that's going to support those answers I gave you. The way you read this is the y-axis is the number of gastrointestinal or GI episodes per 1,000 people. You could also look at this as one surfer surfing 1,000 times. And that the illness rate when they're not surfing is about 18 cases, 18 per 1,000 cases of GI illness, right? And that's about a very common background illness in the population. About 2% of the population will have a GI problem at any given time, right? So GI is like diarrhea mixed with fever or nausea, cramps, something like that. That's how that's defined, GI. And it turns out that when you go surfing during the winter, but it's not raining, it's more than 3 days away from a rain event, which is how the county public health defines it, it goes from 18 to 25 episodes. 25 episodes per 1,000 people. And then if you go surfing the day of the rain or within 3 days after, it jumps up to 30. So when I say, yes, there's risk just going in the water, and that risk increases during wet weather, this is exactly what I'm talking about. So the way it's really looked at is not 30 per 1,000. It's actually the excess illness. So you just essentially back out the not surfing or the not exposed population, and you really look at the excess risk, which is 12 illnesses, right? It's just 30 minus 18. And it's actually 12 extra illnesses or excess illnesses per 1,000 people, which is, if you're a surfer, probably not good. But if you look at relative to the EPA standards, their guidance for their current water quality criteria is an allowable 32 excess illnesses per 1,000. So when I say, yes, there's an increased risk when you go in following wet weather, and that it's not as big a risk as one would expect based on the standards. This is one example of that. So I want to give just a few little nuggets. They're not really questions, but they're interesting findings that we were able to tease out of the data. The first one is helps support the concept that no, it really is wet weather that's causing problems, not a spurious difference. And this is one of those examples. We have the same x-axis, the same y-axis, which is excess cases of GI illness per 1,000 people, and specifically during wet weather. And then we just reran this analysis a number of times. We ran it the day of rain, which would be day 0, the day of rain plus 1 day, the day of rain plus 2 days, the day of rain plus 3 days, right? And so our primary analysis is plus 3 days because that's how the county health departments define it, and that's how it's defined in their TMDL. But you can see if you go closer to the day of rain, you have a higher risk. Of course, you got larger error bars because you have fewer people exposed. But by the time you get to day 3, it's starting to kind of get back down to that baseline illness rate of 18 per 1,000. So this tells me, yes, there probably really is wet weather that's causing, whatever in the wet weather is probably causing the problem. The other interesting part is that the GI illness here on the y-axis, so it's the same unit, same everything, except for this time we looked at size of storm. And it turns out the bigger the storm, the bigger the risk. So in our case, small storms are defined as something less than a ½ inch. Medium storms were between a ½ inch and 2 inches, and the large storms were greater than 2 inches. So the bigger the storm, the more illness you have in that 3-day window. All the more reason to go, okay, that makes sense. The last thing I wanted to show I told you we collected a variety of symptoms, but I only show you gastrointestinal illness. It turns out there's other symptoms that are as bad or worse, right? Things like sinus, skin rashes, and especially in wounds, open wounds that get infected. I think the strongest thing about this plot is that um, all of the symptoms are greater than 1. Right? So this is a slightly different unit on the y-axis. It's an adjusted risk ratio. So the way you'd look at this is the risk of going in the water following rain versus not going in the water. And if the risk is exactly 1, that means the risk of wet weather and not going in the water is exactly the same. But if it's greater than 1, then there's a greater risk during wet weather. And all of these are greater than 1. So it's interesting also that when I do talk to surfers, they talk about ears and sinuses and infected wounds as their worst. And that's just anecdotal. But the data supports that. But it also turns out that none of our water quality criteria are based on these other symptoms. They're all based on just gastrointestinal illness. So we do see a difference in the water quality as you get further from the discharge point. And so yeah. So I'm going to genericize your question, which is, does distance from the discharge make a difference? And the answer is, it does in water quality for sure. We didn't have enough people at different distances to test that with their illness rates. But clearly distance from the discharge makes a huge difference. Let's get to answer the question that was in my title. So does stormwater actually make you sick? I've showed you a lot of data that shows there's an increased risk and an increased rate of illness when you go in after it rains. Well, we also measured what was in those actual discharges. Right? We measured genetic markers of human fecal contamination. In other words, bacteria that's specific to humans, not dogs, not birds, not some other mammal, humans. We measured that to see if there's actual human inputs. And then we also measured the actual human pathogens, a variety of viruses, as you know, like norovirus, enterovirus, adenovirus, as well as Campylobacter and Salmonella. Right? So these are the primary body contact recreation pathogens from the Center for Disease Control, the CDC. I'll tell you for both of them because we use the same method for both. For the people online, the question is, what's the method? Let's quickly describe the methods for these new measurements. They're all done genetically. And so you have to extract the DNA or the RNA, maybe a little cleanup because stormwater is kind of a dirty, source. And then you go and probe for specific genetic sequences for these particular organisms that are well conserved, and then you amplify those. And so we use a technique called droplet digital PCR, which turns out to be very sensitive and very specific. The question is, how big of a water sample do we use for these? Usually about 4 liters. We've done samples up to 20 liters. So the problem is when you go to stormwater samples, there's so many particles in them. I don't know how it is up here, but ours are really dirty. And yeah, so to filter all those bacteria, you need to put them on a filter before you can extract them. And if you have a lot of sand or dirt, my grandma would call schmutz. So there's this balance between schmutz and volume. So. And I can talk more about these measurements at the end of my talk. I have a few extra slides, but let's get through them. And here's some of the results from those analyses. I put 2 river systems up here because these are the 2 drainages that go to our sentinel beaches. The San Diego River and Tourmaline Creek. And what you get, the first column is that human marker. It's a Bacteroidetes HF183 sequence. And what you can see is we see human markers almost all the time from both channels. And when you look at the viruses, some we never see, like enterovirus. Some we always see, like norovirus. And some we see more in one channel than the other, like the Campylobacter. And for what's worth, this all makes sense to me because first of all, the norovirus, which is, it's the same type of virus as like the cruise ship virus, right? It doesn't kill you, but you feel like you want to die. It makes you that sick. And when we see that, then that explains a lot of the GI illness that we might be having. I mean, it's not a one-for-one because we didn't go and test blood or stool or something like that to make sure that was the etiologic agent, but see it all the time and people are getting sick, so there's a little bit of inference there. But it makes sense with the human marker, which we also see all the time. So when we had the question earlier about how do we know sanitary and storm are actually separate, my point to you is they're not separate. There's something in the system that's contributing these pathogens in these human fecal sources. Okay, so for the folks online, there was the comment was there's probably lots of sources in a watershed, which led us to the next question. Well, okay, all those measurements I just showed you were at the very bottom of the watershed right before it discharged to the beach. Where is it coming from in the watershed? And so we have basically a pretty simple design here that moves along the main stem, in this case the San Diego River, and those are the circles, and the diamonds are the bottoms of major tributaries. And all we did was collect large flow weighted composites over the course of a storm, and we were expecting one of two things, right? It's either, wow, there's a really hot tributary, or it's a systemic thing and it's coming from everywhere. Now, what do you think? All I did was create a schematic of the watershed, so it's the same sites, just as arrows. And the size of the circle is the size of the HF183 concentration. Remember, this is the human marker. Right? This doesn't come from birds, it doesn't come from dogs or cats, it comes from humans. And now it doesn't differentiate between sewage versus septic versus what the folks down in San Diego euphemistically call the urban pioneers. So, okay, I got a couple of chuckles out of that. But there's two ways to look at this graphic. The first one is, oh my gosh, look at that giant circle right there, at Marina Boulevard Drain. And yeah, it's true. There is a giant. That was like that was like a 10 to the 4th sample, right? That's like 20,000 HF183 per 100 milliliters. It's an enormous sample, right? And it's clear there is a very strong human source there. The other way to look at this is every single site has a circle. So for the people that said, oh, it was just a hot spot, well, yeah, they're right. And the people who said, nah, it's systemic, it's everywhere, they're also right. So it's not stormwater that makes you sick, it's human fecal contamination that makes you sick. I've shown you a bunch of science. Now the question is how are managers reacting to that? And the first thing they did, of course, is form these things they like to affectionately call tiger teams. So this is their quick response units to go to that Marina Boulevard drain where that big circle is and go, what the heck is it? And in fact, they did find a cross connection, just as you had described. So they also found people, RVs, dumping their villages. Yeah. And yeah, so they've started cleaning that up. The second thing that they're doing is considering site-specific objectives. So anybody that's familiar with the recent EPA criteria know that they have an off-ramp for site-specific objectives, right? If something unique about your site, where the criteria, their national criteria might not apply, you can do that, and you can do that either through an epidemiology study or this thing they call a quantitative microbial risk assessment, or a QMRA. We did both. Right? The health risk model, we figured we're doing the empirical data collection for the epidemiology study. Let's run one of these health risk models, one of these QMRAs at the same time to validate it. And it turns out it actually validates pretty well. So this is what they're kind of, remember this slide? The one where I kind of gave you the basic answers? This is the one that's generating the discussion about should we create a site-specific objective? EPA says 32, we're seeing 12, and so that's the conversation at the very moment. Should we make it 32? What would What would happen if we wanted to raise the risk level up to 32 per thousand? And we do that with a graphic like this. So the way you read this is there's Enterococcus concentrations along the x-axis, and then the excess illness along the y-axis, right? So this is gastrointestinal illness per thousand people. And so if you want to develop a standard, you just find the amount of allowable illness you want. In this case, I picked 32. You draw over to this regression line, which is our health risk relationship from the surfer health, from this epidemiology, this wet weather epidemiology study with the surfers. And then you draw down to get your Enterococcus level, and it turns out that number is 175. Currently, the EPA standard is 30, a geometric mean of 30, whereas we would be a geometric mean of 175 for the same risk level as they put in their guidance. So you guys tell me, is 175 a lot? Would your neighborhood agree to a geo mean of 175? Nobody, complete silence in the room. So for what it's worth, anytime I've been involved in a site-specific objective, bacteria, metals, any of them, it's this concept between a public perception of reducing risk, a public perception of increasing a number, when it actually is just reassigning it to the same risk level. That's really what it is. And so I'm not arguing you should or you shouldn't. It's about perception. So then again, a lot of the dischargers had a perception they didn't have any human fecal sources in their stormwater because their systems were separate. So anyways, this is how you would get to a site-specific objective. As we look forward, now that we've finished this big study and the results have just gone online, there's a few things that they're really seriously talking about. The first one is their ability to extrapolate. So we did these studies in San Diego, and you guys all came for the same reason. How well does that extrapolate to Puget Sound? I'm going to tell you that there's, in San Diego and in Southern California in general, they're expanding in a couple ways. The first thing is they're looking at how many other beaches in San Diego, how many other beaches in the other counties in Southern California, and they're doing two things. They're doing some more of these source identifications, because now that I've found human sources in their stormwater, they're all wondering if they've got human sources in their stormwater, or was it just those two watersheds because for whatever reason. And then the second thing they're doing is, well, if we're going to do all this extra analysis for human sources, we might as well do one of these health risk models, one of these QMRAs, and see if we come up with the same number or not. So the question for the folks online, the question was, are we using some other tests to help track sources? And so the example that was given was caffeine. So I'll start by saying caffeine can work great. We've used it and works really good in dry weather. So, and we've used a lot of other things, optical brighteners, trace organic chemicals. I'm going to tell you they all have the same basic problem, which is when the signal is really strong, like during a dry weather flow, we've even used the dogs, the poop sniffing dogs, and they were great. But in stormwater, at least where we live, where there's large volumes and things get diluted pretty quickly. So what's your caffeine concentrations? 10 times your detection limit, maybe? So for us, it's like, if it's really strong, it's maybe 10 or even 100 times the detection limit. But some of these bacteria, right, they're in the millions to billions. And so you need something that can get diluted 1 billion times and still be able to detect it to find your source. The only thing that can do that is other bacteria. And so the good thing about the HF183 is it's even more concentrated in your gut than the Enterococcus. So if you've got HF183 in your gut, it's just as concentrated as the Enterococcus, so it kind of track it that way. The beauty of the HF183 is that it doesn't survive very long in the environment. Right? It's one of these bacteria, unlike Enterococcus, that can handle air. The HF183 is an obligate anaerobe. As soon as it hits air, it starts to die. So, and then we just speed up because we've been actually able to show we don't have to wait a day or 2 or 3 or a week to get a result with since it's all genetic, we've actually been able to take a sample in the morning, have answers within an hour. So we've automated, in fact, we're getting to the point where we've miniaturized these genetic tests so you can fit them in a suitcase and throw them in the back of your work truck and kind of work your way up a watershed. So that's some of the future. When you talk about looking ahead, that's the future. So there you go, my last slide. And the question was how much per test? For the genetic tests, you mean? Well, it depends on which genetic test. For the HF183, it's about $300 a test maybe. So it's about double what you would charge just for a routine, fecal indicator bacteria test. And as the technology gets more and more commercialized, I think it's going to get cheaper and cheaper as more and more companies enter the market with. Right now, there's only a couple of companies that build some of this digital PCR technology. Do we have any, in this case, scientific evidence of the impacts from the homeless populations? What they might be contributing to the overall bacteria load or pathogen load or both? Okay. So there's been a lot of studies that have tried to look at this impact, and I can tell you that in California, particularly in Southern California, they're getting really proactive. There's one group of folks that are trying to house the homeless and spending a lot of money on that, and then there's another group that are trying to essentially outlaw the homeless. So I'll just give you an example. So we have a Skid Row in LA, and unfortunately, there's a lot of people that live there. And the city took up a policy of, I think it was twice a week, coming in with big wash trucks because it was so much fecal contamination. Literally just washed the whole alley. They don't do that anymore. So one of the things we're going to be doing on the San Diego River in this upcoming winter is specifically trying to target the homeless camps. In this case, they have the encampments along the river, and seeing if we can tease out a signal from the encampments, because they're really now specific objective. EPA says 32, we're seeing 12, and so that's the conversation at the very moment. Should we make it 32? What would happen if we wanted to raise the risk level up to 32 per thousand? And we do that with a graphic like this. So the way you read this is there's Enterococcus concentrations along the x-axis, and then the excess illness along the y-axis, right? So this is gastrointestinal illness per 1,000 people. And so if you want to develop a standard, you just find the amount of allowable illness you want. In this case, I picked 32. You draw over to this regression line, which is our health risk relationship from the surfer health, from this epidemiology, this wet weather epidemiology study with the surfers. And then you draw down to get your Enterococcus level, and it turns out that number is 175. So currently, the EPA standard is 30, a geometric mean of 30, whereas we would be a geometric mean of 175 for the same risk level as they put in their guidance. So you guys tell me, is 175 a lot? Would your neighborhood agree to a geo mean of 175? Nobody, complete silence in the room. And so for what it's worth, anytime I've been involved in a site-specific objective, bacteria, metals, any of them, it's this concept between a public perception of reducing risk, a public perception of increasing a number, when it actually is just reassigning it to the same risk level. That's really what it is. And so I'm not arguing you should or you shouldn't. It's about perception. So then again, a lot of the dischargers had a perception they didn't have any human fecal sources in their stormwater because their systems were separate. So anyways, this is how you would get to a site-specific objective. So here's my last slide. as we look forward, as now that we've finished this big study and the results have just gone online, there's a few things that they're really seriously talking about. The first one is their ability to extrapolate. So we did these studies in San Diego, and you guys all came for the same reason. How well does that extrapolate to Puget Sound? I'm going to tell you that there's, in San Diego and in Southern California in general, they're expanding in a couple ways. The first thing is they're looking at how many other beaches in San Diego, how many other beaches in the other counties in Southern California, and they're doing two things. They're doing some more of these source identifications, because now that I've found human sources in their stormwater, they're all wondering if they've got human sources in their stormwater, or was it just those two watersheds because for whatever reason. And then the second thing they're doing is, well, if we're going to do all this extra analysis for human sources, we might as well do one of these health risk models, one of these QMRAs, and see if we come up with the same number or not. And the question was, are we using some other tests to help track sources? And so the example that was given was caffeine. So I'll start by saying caffeine can work great. We've used it and works really good in dry weather. So, and we've used a lot of other things, optical brighteners, trace organic chemicals. I'm going to tell you they all have the same basic problem, which is when the signal is really strong, like during a dry weather flow, we've even used the dogs, the poop sniffing dogs, and they work great. But in stormwater, at least where we live, where there's large volumes and things get diluted pretty quickly. So what's your caffeine concentrations? 10 times your detection limit, maybe? So for us, it's like, if it's really strong, it's maybe 10 or even 100 times the detection limit. But some of these bacteria, right, they're in the millions to billions. And so you need something that can get diluted 1 billion times and still be able to detect it to find your source. The only thing that can do that is other bacteria. And so the good thing about the HF183 is it's even more concentrated in your gut than the Enterococcus. So if you've got HF183 in your gut, it's just as concentrated as the Enterococcus, so it kind of track it that way. The beauty of the HF183 is that it doesn't survive very long in the environment. Right? It's one of these bacteria, unlike Enterococcus, that can handle air. You know, the HF183 is an obligate anaerobe. As soon as it hits air, it starts to die. So, and then we just speed up because we've been actually able to show we don't have to wait a day or 2 or 3 or a week to get a result with since it's all genetic, we've actually been able to take a sample in the morning, have answers within an hour. We've automated, in fact, we're getting to the point where we've miniaturized these genetic tests so you can fit them in a suitcase and throw them in the back of your work truck and kind of work your way up a watershed. So that's some of the future when you talk about looking ahead. So for the folks online, the question was how much per test? For the genetic tests, you mean? Well, it depends on which genetic test. For the HF183, it's about $300 a test maybe. So it's about double what you would charge just for a routine, fecal indicator bacteria test. And as the technology gets more and more commercialized, I think it's going to get cheaper and cheaper as more and more companies enter the market with. Right now, there's only a couple of companies that build some of this digital PCR technology. Do we have any, in this case, scientific evidence of the impacts from the homeless populations? Is that what they might be contributing to the overall bacteria load or pathogen load or both? Okay. So there's been a lot of studies that have tried to look at this impact, and I can tell you that in California, particularly in Southern California, they're getting really proactive. There's one group of folks that are trying to house the homeless and spending a lot of money on that, and then there's another group that are trying to essentially outlaw the homeless. So I'll just give you an example. So we have a Skid Row in LA, and unfortunately there's a lot of people that live there. And the city took up a policy of, I think it was twice a week, coming in with big wash trucks because it was so much fecal contamination. Literally just washed the whole alley into the storm. They don't do that anymore. One of the things we're going to be doing on the San Diego River in this upcoming winter is specifically trying to target the homeless camps. In this case, they have the encampments along the river, and seeing if we can tease out a signal from the encampments. Because they're really, now that we've been able to demonstrate there's human sources in their stormwater discharge, the city and the county are obligated to go figure out what those are and remediate them. And so they're struggling right now. You know, if it's just a big hotspot like that Marina Drain and they could find a cross connection to a local restaurant, then those are easy. The rest of that systemic lower level is much harder. And so that's one of the theories, is it could be the homeless. So we're tracking that down. The other is it's just, even though the two systems are sanitary and storm drain are separate, there's a lot of what we call it I&I, right? So, you know, where the stormwater gets into the wastewater system, it leaks in either through a manhole or cracks in a joint or something like that, pressurizes the system enough that it'll exfiltrate. And the current thinking is, yeah, but what's the big deal? It's got to travel through a bunch of soil before it'll ever get to a receiving water body. Well, no, not really. It turns out when they lay the streets, they put both pipes in the same trench and fill it with a gravel bed. And the gravel bed becomes a great hydrologic conduit. So, and it'll just travel down that without really any treatment. It actually kind of probably likes it. It's a little cold. There's not much filtration. There's no sunlight. And it'll just go until it finds a weak point, which will either be into a storm drain if there's another crack, or into a receiving water near a head wall or something as it discharges. The question was, is there an actual correlation between homeless populations and bacteria levels? And the answer is no, mostly because nobody has a good count of the homeless population. The salt water caused the bacteria to die off. All right, Edward, so the answer is most definitely. We've done some bacteria die-off studies, both with Enterococcus, the coliforms, and with the HF183, and yet none of those bacteria like salt. And so that, remember how I talked about how the county has this 3-day rule when it follows storms, close the beach for 3 days? They base that all on bacteria levels in the ocean. And that's all because the Enterococcus, its kind of half-life is about 24 hours in salt water. So after 3 days, you really can't measure it anymore. HF183 dies a lot faster. The viruses probably, it kind of takes them a little bit longer. So, but yes, they don't like salt water at all.